Physics for Ravens. The title of today's video is Atomic Structure. So, most people know what atoms are, so this is just a brief refresher. What are atoms made of? Protons, neutrons, and electrons. Inside every atom at the center is a nucleus made of protons and neutrons. What is the word for protons and neutrons? The answer is nucleons. And what is orbiting the nucleus? The electrons. This model of the atom is called the nuclear model of the atom. There were models of the atom before this one, but this is the one that we use today. So, let's picture an oxygen atom. An oxygen atom has a nucleus with 8 protons, some amount of neutrons, probably 8. And if it's a neutral oxygen atom, it will be surrounded and orbited by 8 electrons. And the electrons will be arranged in shells. 2 of them will be in the first shell, which is closest to the nucleus, and the remaining 6 of them will be in the second shell, which is further away from the nucleus. The particles that make up the atom have different properties. The protons, neutrons, and electrons have different properties. Their charges and masses are super tiny, so we have to make up new units that are appropriate for them. For example, the proton and the neutron both have a mass of 1.67 times 10 to the minus 27 kilograms. But this is an absurdly small mass, and so the new unit that we make up is the atomic mass unit, AMU, and we say that a proton has a mass of 1 and a neutron has a mass of 1. What about an electron? An electron is much less massive than a proton and a neutron. The mass of an electron is around 9.11 times 10 to the minus 31 kilograms. This is absurdly tiny, so let's put it in AMUs. How big is that figure? Well, for the proton and neutron, they were 10 to the minus 27-ish kilograms, right? And the electron is 10 to the minus 31 kilograms-ish. So, what? Between 1,000 and 10,000 times less? That's right. So, the relative mass of an electron is 0.0005, about 1/2000th the mass of the proton and neutron. Okay, and what about their charges? What's the charge of a proton? What's the charge of a neutron? And what's the charge of an electron? For a proton, it's +1. For a neutron, it's 0. And for an electron, it's -1. Can you compare that to a coulomb? Yes, indeed. For a proton, the charge in coulombs is 1.6 times 10 to the minus 19 coulombs. 1.6 times 10 to the minus 19 coulombs. Now, if an electron has an equal but opposite charge to a proton, what would the electron's charge be? Negative 1.6 times 10 to the minus 19 coulombs. That makes sense. and the neutron has a relative charge of 0. What is the proton number? Sometimes called the atomic number. This is the number of protons in the nucleus. But what is the symbol? The answer is Z. Z. Perhaps it comes from the German word Zahlen, which means like number or integer. It could do, but I don't know for sure. It's the proton number which actually defines the element that you're thinking about. So an oxygen atom is defined to be an atom with 8 protons. Neutron number and electron number can vary, and we have words for that. But an oxygen atom is defined to be an atom with 8 protons. So, in a neutral atom, the number of electrons is equal to the number of protons. That much is clear. And what determines the element's chemical behavior? The element's chemical behavior is dependent upon the structure of the electrons, the number of electrons that it has, and their arrangement around the nucleus. So, for a neutral atom, the proton number does tell you quite a bit about its chemical properties. Now, what is the nucleon number, also known as the mass number? This has a symbol of A, capital A, and it tells you how many protons and neutrons you have all together, because remember, the word nucleon is used for proton and neutron. Protons and neutrons are nucleons. Okay. So, what is an isotope? What is an isotope? Atoms which have the same number of protons but a different number of neutrons are called isotopes. Isotopes of each other. So, what is a key example of isotopes? Well, let's start with the simplest element of them all, hydrogen. Hydrogen has 3 natural isotopes. 3 natural isotopes that occur in nature. Hydrogen, or protium, deuterium, and tritium. Hydrogen, deuterium, and tritium. Hydrogen, like the dominant isotope, has 1 proton and no neutrons. Deuterium has 1 proton and 1 neutron. Tritium has 1 proton and 2 neutrons. Now, if you change the number of neutrons, does this affect the chemical properties? Basically, no. But it does affect the stability of the nucleus. If, like, you can't just keep on adding more and more neutrons to a nucleus. Eventually, it becomes unstable. And unstable nuclei may be radioactive and decay over time into different nuclei that are more stable. Wait, what is the word nuclei? Oh, it's the plural of nucleus. Okay, so I mentioned radioactive isotopes. Radioactive isotopes, you can use these to find out how old stuff is. Okay, so all living things, me included, contains some amount of carbon-14, a sort of fixed percentage taken from the atmosphere. And when a living thing dies, like when I die, the amount of carbon-14 inside me will decrease over time because it will decay into more stable elements. Scientists can calculate the approximate age of things that they find in archaeological digs that are made from organic matter, like wood or bone, by using isotope data or isotopic data, right? Finding out how much of each isotope is present. And they can find out how much radioactive carbon-14 is left in the object. Now, what is the specific charge of a particle? That, by the way, is a piece of terminology. Specific charge. What is the specific charge of a particle? It's the charge of the particle divided by its mass. The charge of the particle divided by its mass. So, what would the units be then? Well, the unit for charge is coulombs. The unit for mass is kilograms. Therefore, the unit for specific charge would be coulombs per kilogram. Okay, that makes sense. So, what would the specific charge of a proton be? Well, do you remember the numbers from earlier? What was the charge of a proton? It was 1.6 times 10 to the minus 19 coulombs. 1.6 times 10 to the minus 19 coulombs. And what was the mass of a proton? 1.67 times 10 to the minus 27 kilograms. So you do charge divided by mass, divide that first number by that second number, and you get 9.58 times 10 to the power of 7 coulombs per kilogram. Okay. So you could be asked to find the specific charge of a particle, like a fundamental particle, like an electron, or maybe the nucleus of an atom, or an ion, like what about an alpha particle, for example? What is an alpha particle? It is the nucleus of a typical helium atom containing 2 protons and 2 neutrons. Stick them together and that is an alpha particle. So, how would you find the specific charge of that? You need to find the charge of the alpha particle and then divide it by the mass of the alpha particle. Now, how could we just modify the number that we calculated earlier to get that? Because, let's see, an alpha particle would contain 2 protons, right? Okay, so the number would be twice as big, but wait, an alpha particle is 4 times as massive as a proton. Oh, okay, now the number is going to become 4 times as small. Okay, 2 times as big, 4 times as small. Oh, right, so the specific charge is half. Does that make sense? I hope that makes sense. Okay, so next time I will talk about nuclei stability, the stability of nuclei. And that sort of wraps up this short session here.